we introduce canonical policy, a framework for learning canonical 3D representations for equivariant policy learning. It enables vision condition policies to generalize to unseen object appearances and camera viewpoints, while significantly improving sample efficiency. Here's how the canonical policy works. Input point clouds are first centered and pass through an SO3 equivariant network to estimate object rotations. These rotations are used to obtain canonicalized point clouds. A point cloud encoder then aggregates these representations. At each diffusion time step, robot states, position, orientation, and gripper are transformed into the canonical frame via an SE3 inverse transformation. Noisy actions are also mapped into the canonical space, and the model predicts canonical actions, which are finally transformed back to the original observation frame. This figure further illustrates two key modules of our pipeline. On the left, the data canonicalization pipeline uses an SO3 equivariant encoder to align input point clouds to a shared canonical frame. This ensures that rotated or translated inputs map to the same canonical representation, enabling policies to generalize across geometric variations. On the right, the neighborhood aggregation module captures local geometric features by normalizing point positions, applying affine transformations, and extracting permutation-invariant features via residual MLP and max pooling. We benchmarked canonical policy and several point cloud baselines across 12 simulation tasks. Canonical policy consistently outperforms all baselines, achieving an average task success improvement of 18%. We validate canonical policy on 4 real-world manipulation tasks, covering 16 evaluation settings involving distribution shifts in object appearance, shape, camera viewpoint, and robot platform. We conduct 4 real-world manipulation tasks on the Franca platform, namely block stacking, shoe alignment, can insertion, and table organization, are shown in 3 stages: initial, intermediate, and final. Both RGB image observations and point cloud observations are visualized to illustrate the input modalities used by the policy. In the block stacking task, the robot stacks an I-shaped block onto a T-shaped block. On the left, under the original setup, the canonical policy performs reliably. On the right, even with changes in block color, the policy continues to execute the task accurately, showcasing robustness to appearance shifts. Next is the shoe alignment task, where the goal is to pick up the right shoe and align it side by side with the left shoe. The policy succeeds under the original setup on the left, and maintains high performance even when the shoe color is completely changed on the right, demonstrating strong appearance invariance. The can insertion task is more precision demanding. The robot must pick up a can on the right, and insert it into a hole on the left. Despite the challenge, canonical policy consistently succeeds under both the original and color-shifted settings, validating its grasping and placement accuracy. Table organization is the most complex task, requiring a sequence of precise operations, object placement, and drawer manipulation. Canonical policy handles this long-horizon task effectively in both the original and color variant setups, highlighting its capacity for robust, multi-step decision-making. Beyond color variations, we also test shape generalization in the shoe alignment task. By introducing unseen objects, leather shoes and hiking shoes, with both appearance and geometric shifts, we test the policy's ability to generalize. Despite these challenges, canonical policy achieves the highest alignment accuracy, demonstrating strong generalization to both shape and color shifts. For more comprehensive and quantitative comparisons of different policies across various tasks, please refer to our paper. We further evaluate the policy's SE3 equivariance using a mobile UR5 platform with camera viewpoint shifts. As the camera gradually rotates from the original angle on the left to a significantly shifted one on the right, canonical policy maintains stable and accurate predictions, confirming its robustness to egocentric view changes. In summary, canonical policy is a principled framework for 3D equivariant imitation learning. It unifies point cloud observations via canonical representation and leverages generative models like diffusion to enable end-to-end learning, robust generalization, and efficient sample usage. Our contributions span theory, architecture, and extensive real-world validation.